In the late 1600s, Newton made a great buzz with his law of universal gravitation, which is the following. Any two objects of mass m1 and m2 and separated by a distance d attract each other with a force F given by this expression, g, the constant of universal gravitation, times the product of the two masses and divided by d squared. That's one of the most important laws of physics, but where does it come from? First, we have to agree that this part of the expression is quite intuitive. Indeed, mass is the source of gravity, so we expect the force to be proportional to the mass of both objects. But let's show this more formally. So we start again with our two masses m1 and m2, which attract each other with a force F. Now imagine that we add a second little mass m1 next to the first one. This new mass is attracted by the mass m2 with the same force F, and m2 is also attracted by this new mass with the force F. But we can also consider those two masses m1 as just one object of mass 2m1. And because forces add up, this object is attracted by the mass m2 with the force 2f, and same thing for m2. So in the end we find that if we double the mass m1, the force is doubled. So we infer that the force is proportional to m1, and we can use the same argument for m2. So that was for the mass dependency, and we also expect the constant to be here, because this term, once determined, doesn't have the same units as a force, so we need a constant to match the units. So the whole mystery here is in the distance dependency. Why is it d squared and not d or d cubed or exponential of d or any other function? To answer this, I went to the ultimate source, which is the Principia of Newton. And precisely the answer is at proposition 4, corollary 6, where we can read this. If the periodic times are in the sesquiplicate ratio of the radii, and therefore the velocity is reciprocally in the subduplicate ratio of the radii, the centripetal forces will be in the duplicate ratio of the radii inversely. Old books are often difficult to understand, so let's try to express this in modern terms. He's actually talking about planets, so let's consider a planet which rotates around the Sun on a circular orbit at a distance d and with a speed v. Now the force of gravity acts on this planet, that's what keeps it on its orbit, and we want to find an expression for this force. So the first advantage that Newton has here is that he defined the notion of force. He said force is mass times acceleration, because there was no formal definition of force before Newton. So now we have a definition for the force, and we know the motion by assumption here. We assumed a cycle. So if we just apply this definition in this particular case, we find this expression, m times v squared over d. This we find it just by geometry, and I don't show it because it's not the most interesting. And that's it, we have a first result. That's actually what Newton says at the start of proposition 4. He says the centripetal forces of bodies, which describe different cycles, tend to the centers of the same cycles, and are one to the other as the squares of the arcs described in equal times applied to the radii of the cycles. So in those days they always talked in terms of proportions, so he considers different cycles, and he says how the forces relate to one another on the different cycles. So we have this result, but it's not really satisfying because we have an expression which depends on the distance, that's good, but it also depends on the speed, and the speed must also depend on the distance somehow, but we don't know how. So before going further, let's re-express this in terms of the orbital period. That's the time that the planet takes to go around the Sun. So we rewrite the speed as the total distance traveled, which is 2 pi d, and divided by p, which is the orbital period. And if we insert this in our expression, we find that the force is proportional to d over p squared. So here I just re-expressed the force in terms of p, but we still have the same problem. We want an expression that depends only on d, and actually we won't be able to achieve this just from pure theoretical arguments. Here we have to use an empirical result, which is the third law of Kepler. Kepler found that p squared is proportional to d cubed. And that's exactly what we need here. That gives the relation between the orbital period and the distance. And if we insert this in our last relation, we finally find that the force is proportional to 1 over d squared. So that's corollary 6. If the periodic times are in the sesquiplicate ratio of the radii, sesquiplicate means to the power 3/2, and therefore the velocity is reciprocally as the subduplicate ratio of the radii. Subduplicate means 1 over square root. This is an intermediate result that we haven't used, and the centripetal forces will be in the duplicate ratio of the radii inversely. So that means the force proportional to 1 over d squared. So to summarize, we started from the definition of the force, then we applied it to the case of planets and applied some geometry to find an expression that depends on the orbital period and distance. And finally we used an empirical result, which is the third law of Kepler, And we found the distance dependency of the force. And that's it. Thanks for watching.